video, I'll be covering about the Wien bridge oscillator, which is another type of oscillator. In the last video, I have explained about the ladder network oscillator. So now we have another type, which is a Wien bridge oscillator. Wien bridge oscillator is a type of oscillator where we are going to connect the resistors and capacitors in a bridge pattern. Okay, so here we have a 4 terminals A, B, C, D. A and B terminals are used to apply the input, whereas the terminals C and D are used to taken out the output from the Wien bridge oscillator. Okay, so this Wien bridge oscillator will also produce a phase shift of 0 degree. Okay, for a sustained oscillations we require a 0 degree or a 360 degree phase shift in an oscillator. So this Wien bridge oscillator produces an 0 degree phase shift value, and here we are going to make use of the gain equation, which is given as AV, it is equal to 1 plus C2 divided by C1 plus R2 divided by R1. Okay, so this is a gain equation, that is a minimum gain of a Wien bridge oscillator. And coming to the frequency of oscillation equation in the Wien bridge oscillator, it can be written as F is equal to 1 divided by 2 pi square root of R1, R2, C1, C2. Okay, so this is an expression. If you assume that R1 and R2, C1 and C2 are equal values, then we can rewrite this expression as if C1 is equal to C2 and R1 is equal to R2, then this equation becomes F is equal to 1 divided by 2 pi square root of R square into C square, that is which is equal to C, and here I will make it as R. Then the final expression becomes 1 divided by 2 pi RC. So this is an frequency of Wien bridge oscillator, and by taking a simple values for R and C, easily you can calculate a frequency, which are the basic problems which can be asked based on the Wien bridge oscillator. Okay. So after the Wien bridge oscillator, we have a concept called multivibrators. What are multivibrators? The name itself is saying it is multivibrator. That is multivibrators. Multivibrator, that means multiple vibrations. So multiple vibrations in the case of oscillators are produced, and that oscillators are called as multivibrators. And the multivibrator will produce a waveform in the form of square wave or in the form of rectangular pulses. So multivibrations includes the major 3 types. The first type is astable multivibrator. Second one is monostable multivibrator, and the third one is bistable multivibrator. So what is a astable multivibrator? Astable multivibrator will continuously produces a square wave, and it is also called as free running multivibrator. Since it continuously produces the waveform, it can also be called as free running multivibrator. Next we have a monostable. Mono, it is, as the name itself is indicating, it is going to have a one stable state, and it is going to produce a one cycle of pulse, and it is also called as one shot multivibrator. Okay, and next we have a bistable multivibrator. So bi means it is having 2 stable states, and in the bistable multivibrator, in order to change from one state to another state, the waveform should have a control signal. Okay, and these are the types of multivibrators. So though we have these 3 types, in the syllabus of introduction to electronics, we have a type of multivibrator which is a single astable multivibrator. Single astable multivibrator. So the single astable multivibrator circuit is like this. It's going to use a op-amp. So this is an op-amp. So this is provided with the positive feedback. See here. So we have applied some portion of output which is fed back to the non-inverting terminal of op-amp. Okay. So here this is contributing for positive feedback which is given through the potential divider circuit. So these two are combinedly forming a potential divider circuit and it is fed to the non-inverting terminal through this network. So after that we have a R value here. So why the R is used? So that resistance is used in order to change or in order to adjust the frequency of astable multivibrator. So in order to analyze this particular circuit, so let us assume that initially we have a capacitor which is uncharged. Okay. So and we know that it is a multivibrator circuit. It's going to produce a square wave like this. Okay. And square wave so it's going to produce a square wave like this, and when this capacitor is uncharged, we assume that the voltage in the non-inverting terminal is more than a inverting terminal. In that case, the output voltage whatever we are going to get, so it will be rise to the plus VCC. So it's going to rise like this. Okay, and this rise is called as upper threshold. And whenever, as soon as this reaches a plus VCC, the capacitor will start to charge. And when it's going to charge, the output voltage of the value will be start decreasing. And when it's going to be charged, the output will be start to exponentially decrease to the minus VCC like this. Okay. So when it's dropped to the minus VCC, the capacitor will start to charge in the opposite direction. Okay. So this is an operation of astable single multivibrator. It's going to have a two threshold values with respect to voltages. One is upper threshold and another one is a lower threshold value. Upper threshold is given by since it is charging up to plus VCC, we can take it as plus VCC into R2, that is a potential divider value, R2 divided by R1 plus R2. Okay, so this is the upper threshold value. So coming to the lower threshold value, it is VLT is equal to minus VCC R2 divided by R1 plus R2. And the time constant here it is given by T is equal to 2CR natural log of 1 plus R2 divided by R1. Okay, so these are the equations you need to remember in the case of single state multivibrator. Okay, so initially the capacitor will be uncharged and the output voltage will be rise up to plus VCC, which provides an upper threshold value. And when the capacitor will start to charge whenever the non-inverting terminal voltage is less compared to inverting, then it's going to charge. In that case, suddenly the output will drop to minus Vcc and it's going to produce a lower threshold which is provided by this equation. And overall time constant of this particular circuit is given by this equation. Okay. So after that we have a last type of oscillator which is called as a crystal oscillator. Okay. So why we go for a crystal oscillator? So crystal oscillator will be used whenever we need a exact frequency. So crystal means it is nothing but a quartz crystal, and here the crystal will be having two phases like this, and every time we are going to have a potential difference between these two phases of crystal, and this effect is called as a piezoelectric effect. So from this effect we are going to get the exact frequency in the oscillations which are produced in the oscillator circuit. Okay, and this crystal oscillator, it works in two different modes. The first mode is fundamental mode, and second one is overtone mode. Okay, so in fundamental mode it works with a frequency range of 100 kilohertz to 20 megahertz, and in an overtone mode it works for 20 megahertz to over of 100 megahertz. Okay, so these are the frequency ranges of fundamental mode and overtone mode. So we don't have a much concept about this crystal oscillator. According to the syllabus, we have the crystal what going to use in a crystal oscillator and why it is required. It is required to have a exact frequency of oscillations, and it's going to operate in a two modes, fundamental mode and overtone mode, and with the frequency ranges from 100 kilohertz to 20 megahertz and 20 megahertz to 100 megahertz. So this is a concept of oscillator and multivibrators.